Today I'm going to be talking about forging techniques, and when I mean forging techniques, specifically today we're going to be talking about tapering. This is opposed to bending, where we're moving steel in sort of a 3D space. This time we're forging tapers, so we're changing the cross-sectional area, gradually going down to a point. We're going to split the video into sort of two halves. The first half we're going to talk about the theory and sort of the science and the physics behind all of this. My dad, who is usually the person behind the camera, has a PhD in physics, and so was very knowledgeable on all of the equations and all of that stuff. And then the second half of the video is going to be sort of a more practical demonstration, putting the theory into practice in forging out tapers. I'm going to quickly speak a little bit about the anvil, how we can use this when forging out tapers. It's all about surface area contact. So you reduce the surface area contact, and we'll do all of this in the theory in a minute and explain why this actually works and why you can draw tapers out much more effectively. But if you reduce the surface area contact, you will draw, taper, and move material quicker. And so to do that, often we come over the far edge of the anvil, as you can put the steel like this, almost a 45-degree angle is like a really aggressive angle. Usually you might come a little bit lower to a 30 or 25 degrees. Really reduce that surface area contact and draw that steel out. And then when you're onto, say, finishing stages, you come down and you go onto the face of the anvil, if you then have a much larger surface area contact, so you can planish all the surfaces and get it all nice and neat. Instead of coming over the far edge of the anvil, what you can do is you can come onto the horn. As this is spherical or a cone, you can reduce that surface area contact a little bit like a curve-faced hammer or a rounding hammer, as it is that sort of dome or that cone shape. There's more surface area contact on the horn rather than the far edge, where there is less. So that's why a lot of people will go over the far edge rather than on the horn. Although it can be quite useful if you want to have a smooth transition between two tapers. So say you have a big lump of material on the end of a bar, and a big lump of material here, and you want a taper that goes from big to little, little to big. The horn can be quite useful for that. Anyway, let's get onto the theory. Okay, hopefully this isn't going to take too long. I'm going to try and explain what's going on. We use a couple of different equations to get what I'm trying to show you. The main one is pressure. So the pressure is what we're going to exert on the steel to move it, equals force over area. Force is equal to the mass times the acceleration, and in this case it's the deceleration of when you deform the steel. So when a hammer comes down and hits a piece of steel, how much does that deform, and what is the deceleration as that deformation happens? Acceleration is dv by dt, which is the change in velocity over the change in time. So velocity is dx by dt, and here dx is the change in distance and dt is the change in time. All right, it's getting a little bit more complicated now. We've got this equation. So x is now the integral of v dt. Stay with me. I'm going to draw a little graph so you can sort of visualize this particular equation a little bit better. Let's say that we started at this velocity and we are changing, that velocity is gradually decreasing over this time. So you can see we've got the velocity and then the change in time. And so the integral is just this area. And here we've done this as a linear, directly proportional change in velocity to time. However, that's probably not very accurate, but as just a rough estimate, that's what we've done it as a linear, directly proportional line. We can then create this equation where we have the distance is equal to half v0 delta t. Delta t is then equal to 2x over v0. So you can see now we've got delta t, which is the same as this little guy over here, dt. They mean the same thing, change in time. So we can substitute this equation back into the bottom of this one. So I'll rub it out and then rewrite that. This was the original equation. Acceleration is dv over dt, but we can rewrite this just as that v0. We can put that little bit that we just worked out over there back into the bottom here. We have the v0 on the top from there, then we have a 2x, and then you get another groovy v0 coming on down here, as that was what we worked out over there, which then we can all rearrange into v0 squared over 2x. Now we have an equation for acceleration, which we can put back into the F equals ma, which is the force, which we've got up here, and then the mass times the acceleration. So we can put this equation back into there for the A, so we end up with force equaling the mass, which we know, that's the mass of the hammer, times by the acceleration, which is now v0 squared over 2x. All right, I've rewritten that out. So we've got this equation, just it looks a little bit more groovy as we've managed to get rid of acceleration. So we've got the force equaling the mass of the hammer times by the v0 squared over 2x. So using a few estimates that we've come up with for x and v, we can now work out a rough, very rough estimate for the force of, you know, the force that you're actually going to create when you're bringing that hammer down. This is the hammer that we're going to be using, and this weighs 1.5 kilograms, which is a little under 3.5 pounds, a bit over 3 pounds. The mass is 1.5 kilograms, that's the hammer. The velocity we're estimating is going to be about 12 meters per second, although that is just a rough estimate. And then the deformation distance we're saying is a millimeter. So let's put all those numbers in, quickly work out what F is as a number. This is approximately, you know, it's not quite, but approximately it comes out at 100,000 newtons. The equivalent mass of this is 10,000 kilograms, so you're going to be hitting with a force of 10 tons, which when you think about it is actually, that's quite a lot really, you know, hitting with a force of 10 tons, that's pretty good going. Anyway, we can put that into that top equation, and I can show you that when you hit with the same force, just by changing your surface area contact, you can create a massively different pressure, and so you're putting more pressure into the steel, and so you're moving it at a much faster rate by just changing the area rather than hitting harder. These are our three angles, so we're going to go 45 degrees, 25 degrees, 5 degrees, which is pretty much on the flat of the anvil. So you'll use 45 when you want a really aggressive taper to really draw that material out. 25 you want a bit of a sort of more elongated gradual taper, and 5 degrees on the flat of the anvil when you want to be really a finishing heat, finishing the taper, planishing everything, making it all nice and neat. 3 different equations, and we've got that constant force on the top at the moment, so we need to work out the surface area on the bottom, which is going to be the surface area contact with the anvil on the underside of the piece of steel. There is obviously the surface area contact on the top side of the steel, which is caused by the hammer, which you can reduce by using, say, a curve-faced hammer or a rounding hammer rather than a flat-faced hammer. Now, the numbers that I'm going to be putting in on the bottom of these 3 equations are going to look a little bit strange just because we have to do it in meters squared, not millimeters squared. So I'll also write down here what they are, you know, what I'm actually doing in millimeters, so it looks a bit more, looks a bit more normal. Here are the 3 areas on the bottom. As I was saying, they look a bit groovy. You know, this one's 10 to the minus 2 times 5 times 10 to the minus 3. But that works out at 10 millimeter by 5 millimeter. This one is 10 millimeter by 10, and that last one 10 by 50. So you can see we're gradually increasing our surface area contact as we decrease our angle to the face of the anvil. These are just rough estimates based off the edge on my anvil. Obviously, you know, this is sort of a key aspect of dressing your anvil. You know, you want to dress the edge of your anvil, which will come to that a little bit more on the practical side, and how you can prevent certain things happening and why you need to dress the edge of your anvil. At the 45-degree angle, we create a pressure of 2 times 10 to the 9 newtons per meter square. And just by decreasing that angle down to 25, we halve the pressure. So you can see we've got 2 times 10 to the 9, and here we've got 1 times 10 to the 9 newtons per metre square. And then the final pressure over here, we've got 2 times 10 to the 8. So that's knocked down again quite a lot. So you can decrease that pressure by just changing those angles. Anyway, let's now try and apply all of this to some actual practical demonstrations. Before I was talking about dressing your anvil edge, and what I mean by that is you can see here, this has a nice radius on this edge. So as we're eating away at the material over the far edge, half on, half off with that hammer, so you're hitting over the edge, you create a little lump of material on the underside, which you turn, bring it back slightly, hit again, turn, bring it back, turn, bring it back, and you gradually create a taper moving down, keeping a little sort of nub of material on the end, gradually planishing those other little lumps as they come, and you pull back and rotate with each hit. If you have a sharp edge on your anvil and you're at quite a high angle, you're trying to create a really aggressive taper, what you can do is you can cut into the steel, and then sometimes, if it's really sharp, your anvil edge, you can create cold shuts. Cold shut is basically a fold. I'll draw it out in a minute on the table so you can see it. So imagine this is the anvil. If we have a sharp edge on there, and we have a bar, if we hit there, half on, half off with our hammer, it's our hammer face, half on, half off, hitting on a sharp edge, we're going to create this sort of imprint in the bar steel. I've drawn it exaggerated so you can see it. And what can then happen is, as we're turning that over, tapering out the rest of this bar, is this edge here folds over and folds in like that. Because it's so sharp on there, as you're drawing it out, it can fold in. Then if we planish all of that back, you can see that we'll have a bar like this. So you can see that edge is folding in, and then we'll have a bar like this, and it's got this hidden crack in. And so that is a cold shut. We then draw this down into a taper, into a tapered bar. That cold shut's still there, and it can create stress concentration, and then your taper's going to snap off. So you want to make sure that you have a nice rounded edge on your anvil when you're tapering out bars like this. A sharp edge is very useful for other applications in forging, whether, I can't think of any at the moment, upsetting a certain thing to make a shoulder. A sharp edge on the anvil can be very useful for doing that, but for tapering out bars, you tend to want a much more radius edge. So in forging tapers, you want the steel to be really nice and hot at a good yellow temperature. I'll bring it up high and we'll do the 45-degree taper first. You can see now we've got a nice taper out there, but we want to planish all of those edges down so it's got a nice flat. And to do that, we obviously have to decrease our angle, so we're increasing the surface area of contact. And we can then planish along and move the steel under the hammer. Don't move the hammer, move the steel. Obviously you can work in or work out. So there you go, you've got a nice little short taper on the end of the bar. So that was using the nice high aggressive angle. We'll now take a new bar and do the sort of 25-degree angle, and we'll draw out a much longer, hopefully more elegant taper. Try the 25-degree angle now. There are the two tapers, and you can see the difference in them. Obviously, this one's a lot longer and a lot more gradual. So that was the 25, and this was the 45. And both of these were just done with this hammer, which is the hammer that we based all of the calculations off, which is 1.5 kilos, just under 3.5 pounds. But obviously this has a flat face, and so if you want to be even more aggressive, you can take a curve-faced hammer. So there are hammers which have this slight dome on, and so that then decreases the surface area that you're hitting with over the far edge of the anvil. So it's all, again, all about that surface area contact. This one will be more effective in drawing steel out and moving it. These two tapers are quite long tapers, so if you want to create a really, really short taper, I'll show you how to do that now. And we're, again, going to use that 45-degree angle where we're going to be forging sort of on the face of the anvil rather than half on, half off over the far edge. So we're going to forge a very, very steep point on the end here, working all four sides, rotating each as we go. And it's very important here that as I'm bringing this hammer down, I'm forging into the steel, and I'll explain that in just a little minute. There we are, we've got a nice steep point on the end of that bar. Again, using a slightly different technique of forging in, matching that angle. So whatever angle you want there, you've got to remember that the anvil and the hammer, they're both doing, you know, whatever you do to the top, the anvil's going to be doing to the bottom. So if you have it like this, you're going to forge an offset point. So bringing that angle up, you can forge it so that point remains in the middle of the bar. We've got our anvil here, that's the flat, and then there's the edge and a nice radius. So we're wanting to create a really steep point. To do that, we're going to bring the bar in. So this is our bar. We want to forge with our hammer like this, coming in there. And so whatever we're doing here, the anvil is also going to be doing on the back side. So you've got to make sure that this means that we then create that angle there, which you can see is just parallel to the face of the anvil. And then on this side, we're going to create an angle like that, which is going to be parallel to our hammer face. Some people will forge this particular style of taper by using a glancing blow, and so the hammer is coming down like this, down here, rather than going in. And that's fine when you're doing smaller stocks, so like 10mm, a glancing blow is probably okay, but when you get up to bigger size stocks and you're trying to do a really short, steep taper, say on a 20mm square bar or 16mm square bar, and you're using a glancing blow, and what will happen is you'll just brush the edge over. And the same will happen on here as you're rotating 90 degrees every time. You'll gradually brush each of the corners over. On bigger size stock, you'll create fish lips. And fish lips, again, create a cold shot in the middle of there, which you can't really get rid of other than trying to forge weld, which I suppose on ornamental things is fine. You know, you can forge weld it back shut, but if you want it to actually be, you know, a strong taper, you want it to be a solid piece of steel, I would use the technique where you're coming in rather than glancing across the top surface of the steel. You've got to think of steel as having an inner core and then an outer layer. And so when you're glancing, you're only moving the outer layers, and the outer layers will come round, create a fish lip, creating a cold shot. Whereas if you're doing this, you're forging in, so there's no way that outer layer can come around as you're forging it in on itself. The inner and outer layer, sort of the inner core and outer core, it's just a way of thinking about steel. And it's a really useful way of thinking about it when you're imagining how you draw a taper out over the far edge. If you have the edge of the anvil here, you are you're imprinting into the steel, so you're going through the outer layers into the core. And there's a smith up in Shetland, Bruce, who once said to me that you want to get the steel flowing, so you want to really get into the middle of the steel and draw that out and get it flowing out, breaking through the outer layer into the inner core, if that's how you want to think about it, to draw out that taper. You'll notice as I've been forging out all of these tapers, the end is still quite chunky. It's not down to a fine point. If you have to take another heat in the fire, you're not going to burn that end off. You want to sort of work from the back of your bar down to the end, especially when drawing out a taper in a coal forge. Is you have that, so you've got the fire there. It's about as big as your fist, the hot part, and so you want to be working from the back down to the point. Otherwise, you're going to be ending up with, you know, half the steel through the end of the fire, which you can't do in a coal forge unless you have a lot of space behind it. And so we leave that point till the very end, and I'll show you how you can do that. If you've got a little bit of heat back here, you can work the heat down by hitting a little bit faster and going over the far edge of the anvil, or even doing the 1-2. Just working two sides. You can really heat the steel with a hammer, and that's changing your kinetic energy into heat energy. And we'll do a little equation on changing kinetic energy into heat energy in a little while, so you can see the theory behind this. It's a dull red, so we've just finished tapering it out. It's as if we've just finished tapering it out. Let's see if we can put that heat energy, thermal energy, back into the bar, heating it back up so we can draw out an effective taper. See there, it gets nice and hot. You can draw it out another length. This is the equation that we're going to be using to show the change in temperature. So you can see the change in energy is equal to C, which is the specific heat capacity, times by the mass, times by the change in temperature. So we can rewrite this just by reorganizing the letters to this equation. Energy up here is kinetic energy. The equation for kinetic energy is E equals a half mv squared, m mass, v velocity, E energy. Not all the kinetic energy will go into heating, as some of it will go into deformation of the steel and a little bit into noise and whatever. But the stuff that we want to go into heating, let's call it alpha. We've got delta E equaling alpha times by half mass velocity. So we can put in our numbers from before, just our rough estimates for mass and velocities. Roughly with those numbers, it will give us about 100 joules. If we say alpha, so the amount of energy, kinetic energy going into heating the steel, if we say that alpha is about 10%, that's just, again, an estimate, then delta E is going to be approximately equal to 10 joules, 10% of 100. The specific heat capacity of mild steel, we looked this up, is roughly 500 joules per kilogram per Kelvin. That's the C. I'll write it down. It's interesting, actually. The specific heat capacity changes varying on the carbon contents, and even, I think stainless steel was around 450, and that must be the other elements. You know, it's got quite a lot of chromium in the stainless steel. But anyway, another interesting little thing. We need to measure the mass of the little bit of material on the end of the bar that we're going to heat up. So we've estimated that this here to be about 10 grams, which we're going to have to put into this equation as 10 to the minus 2 kilograms. I'm just going to rub this out so I can then just rewrite this equation. We've got 10 joules over the 500, which is the specific heat capacity, times by the 10 to the minus 2, which is roughly the mass of the piece that we're trying to heat up, and this comes out at 2. When I say 2, I mean 2 degrees centigrade. 2 degrees represents the amount of thermal energy you're putting in from kinetic energy if we're using all the things that we said we were, so a mass of 1.5 kilograms and a velocity of 12 meters per second. In one hit, we'll raise the temperature of that little piece of steel, that 10 gram piece of steel, by 2 degrees. But obviously, that isn't including the heat that we lose from the steel to the surrounding as we are heating it up. So this is if we have a cold piece of steel and we are hitting it continuously for however long, with each hit we will be heating it up by 2 degrees. So we can put this into the practice in that piece that I just did then, where I probably hit it, I don't know, say I hit it 100 times. when I was doing the, the 1-2 method. Hit it 100 times pretty fast. So we would raise it by roughly about 200 degrees, which is probably about right. We went from a dull red to maybe a dull orange, I would suppose. So there's probably a difference of about 200 degrees. There you go. You can see that with this little bit of an equation and specific heat capacity, you can see how we actually take the practical side of blacksmithing. I just use this technique then to heat up that bar of steel so we can draw out a little bit of taper. This shows what's actually going on in the steel itself. There we are. I hope you enjoyed this video. There was probably a lot more theory than practical demonstrations, but this was something that I've been wanting to do for quite a while, to actually explain what's going on when we're forging these tapers using that equation, pressure equals force over area, and how we can keep a constant force but change that surface area contact and then change the amount of pressure and the amount of steel that we're moving with each hit. And then also there's other interesting things, such as, how much heat you are putting in with each hit, and why, when you're doing that, that 1-2 method, why you can heat steel up, why you can put that colour, that heat back into it through that kinetic energy turning into thermal energy. Anyway, thank you for watching this video. Hopefully it didn't turn out too long or too complicated. I hope you could vaguely understand what I was trying to say. We obviously used estimates for a lot of things, like the 12 meters per second for the velocity of the hammer coming down, and other estimates. But thank you for watching the video, and I hope to see you soon.